So we're going to deal with one type of two-dimensional motion, contrary to what the slide says. We're going to deal with projectile motion for the remainder of Chapter 3. So if you're reading Chapter 3, for the time being, let's skip the section on relative motion just for the sake of time constraints. I want to make sure we get through projectile motion before the exam. So nothing concerning relative motion will be on the first exam. So the only 2D problem you might see is some form of a projectile. So we're going to go through a couple examples. I made as many that I thought were similar to the WebAssign, so we get some practice of all three types. So a projectile, and you'll hear me say this a lot, a projectile is moving in the X and the Y direction, but it has two different types of motion. Since we're ignoring air resistance or drag in this course, we've got a projectile that's launched in both the X and the Y direction. It's going to exhibit constant velocity in the X direction. So its velocity is not going to change in the X direction, and the object's going to be free fall in the Y direction. Okay, so if we launch a projectile with some angle from the X axis, it's going to have an initial velocity in the X direction corresponding to V initial cosine theta, and an initial velocity in the Y direction, which is V initial sine theta. Right? V initial is going to be the magnitude of this vector. Right? So we're going to resolve this vector into its X and its Y components. Okay. Then it's going to be launched. It's going to follow a parabolic path, and then it's going to land somewhere else. Right? So we're going to talk about all the cases where this object might land. Okay, so vectors that are acting in the X and the Y direction are independent of each other. So what that means is whatever happens to a velocity vector or an acceleration vector in the Y direction has no impact on an object's motion in the X direction. So that's going to be our strategy. We're going to split these problems up into the X direction, Y direction, and then handle them accordingly. So for the X direction, the motion is uniform. There's no acceleration in the X direction. Right? We're neglecting drag. Drag would cause the object to change its velocity in the X direction, but we're going to neglect that. So the velocity, whatever velocity in the X direction the object is launched with, it's going to maintain that velocity in the X direction. So we only have to apply one equation for the motion in the X direction. Right? And that's my constant velocity equation. Delta X is V delta T. In the Y direction, the object's going to be in free fall. Now again, that doesn't matter if it's got an initial velocity of 0, a positive initial velocity, negative initial velocity. We're going to treat the motion in the Y direction like it's in free fall. Okay, the moment it's in the air, it leaves whatever device is launching it. It's going to have an acceleration of 9.8 meters per second squared. In the negative Y direction, our kinematics equations that have acceleration in it are going to be applicable in the Y direction. So for the first problem, I'll write the equation in the X direction. I'll write all relevant equations in the Y direction, see which one applies, and we'll just solve it like a kinematics problem. Right? Kinematics in the X, kinematics in the Y, and we should be able to get the values we're being asked for. So normally, if we were live, I'd show you an example of this. So take, if you have a tennis ball or lacrosse ball or something at home, so you can take a ball and drop it and time from a certain height and time how long it takes to reach the ground. Right? So maybe if you drop it from the height of a tabletop, somebody at home times it for you, right? T initial, T final. That's a delta T, right? That's the time it takes, right? You can use free fall kinematics, initial velocity of 0, acceleration is g, measure the height, right? You can see all those values should line up with the kinematics equation, right? Because we can neglect air resistance, for some objects. So if I take that same tennis ball, right, take the same tennis ball and roll it across the top of the table so it comes off the side of the table in the x direction, right, you'll see you'll get a pretty similar time, right? In a vacuum it would be identical, but you should get roughly the same amount of time it takes this object to roll off the side of the table and hit the ground as it did when you just dropped it. Okay, so this is an example of the independence of the vector nature in the x and the y direction. Okay, these two objects do the same thing in the y direction regardless of the initial velocity in the x direction. Right, this thing you rolled off the table had a velocity in the x direction, but that was independent of what it did in the y direction. Okay, so that's what allows us to split it up into x and y components and treat the motion in different directions differently. Right, see this velocity vector, right? I'm given a velocity vector v. It's got a y component, it's got an x component. So this x component of the velocity stays the same, right, all the way through the motion. It's 9.8, 9.8, 9.8. But the velocity vector in the y direction starts out positive, gets smaller because we've got an acceleration in the negative y direction. So that's causing the velocity vector in the y direction to decrease. Eventually, max height gets to 0. I don't see a y component of my velocity vector. So it still has velocity at the top, but it's just the x direction. There's no y component of velocity. Then it's going to start to descend because the acceleration is still negative the whole time the object's in free fall, and then it's going to hit the ground. And again, just like with my symmetric free fall problem, the y component is positive, 19.6 in this case, and then it becomes the same magnitude, different direction. Our x component stays the same. So this velocity vector is the same in magnitude, but now it's pointing into the fourth quadrant because that's the direction it's hitting the ground with. Okay, same magnitude. The y component is switched, goes from positive to negative, and then the x component stays the same. So let's start with a nice symmetric problem. So the object is given an initial velocity, right? Now this is a magnitude I'm being given, and this is the direction. So I'm launched from the ground with a velocity of 20 meters per second. The angle the velocity vector makes is 25 degrees with the horizontal, right? So it's 25 degrees above the ground. That's the angle at which it's being launched. It strikes the ground at a vertical position equal to its starting position. Okay, so it's going to end up back on the ground. So we're looking for four things: the max height of the object, the total time the object's in the air, the horizontal displacement, and then the magnitude and the velocity of the object just before it hits the ground. Now there's an easy way to do this because we know it's a symmetric free fall problem, but I'll just go through the motions and show you how we find the final velocity in the x and the y direction, and then we'll have the components, we'll find the magnitude and the direction. Alright, so I've got a magnitude 20 meters per second. The angle is 25 degrees above the x-axis. Okay, so what I'm going to do, first thing, I got magnitude, I've got direction, split it up into its x and y components, because again, constant velocity in the x direction, it's free fall in the y. So I need the x component of the initial velocity and the y component of the initial velocity. So v times cosine theta. In the x direction, I get 18.1 meters per second in the x direction. In the y direction, v sine theta, I get 8.5 meters per second in the y direction. Both components are positive. I'm being launched above the positive x-axis. So a little tiny change in my notation here. V initial y. I've got that, a v initial. I don't have an initial here. So why don't I have a v initial here? Because it's constant. This velocity in the x direction is constant. Only one kinematics equation applies. That's delta x is v delta t. Okay, so v sub x stays the same throughout. I've got free fall in the y direction, so I take my kinematics equations with acceleration in it. I have that other one that has the average of velocities. That might come in handy, so we can play with that if it comes around. So these three kinematics equations I have modified for free fall, right? I've got g in there, I got the negative sign, g negative sign, and then I give all my velocities y subscripts. Okay, so these are my free fall kinematics equations for the y direction, x direction. I've got 1. So what's my max height? My max height, h max, is when the velocity is 0. Now I'm just dealing with, I see this a lot, I'm just dealing with the y direction, so make sure that when you're substituting in for v initial, you're just substituting this value in. Okay, I see some people still plug the magnitude in, so make sure we're using the y component. So v final is going to be 0 at max height. I'm looking for a vertical displacement, so I'm going to use this equation here. I know the initial velocity, got acceleration, I know the final velocity's got to be 0. Set v final equal to 0, solve for delta y. So I'm subtracting v initial y squared from both sides. Don't forget this negative sign here, that still survives. Divide both sides by negative 2g. So I've got a nice expression for the vertical displacement, max height. So plug 8.5 meters per second in for v initial, 9.8 meters per second squared in for g. Calculate it, negative signs go away, so I have a positive displacement, h max, of 3.7 meters. So I did this all using the motion in the y direction. Right? I didn't have to do anything with this because I'm just talking about what it's doing in the y direction. Total flight time. If this is a symmetric free fall problem, I can say the displacement is 0 because it returns back to the ground. So I'm going to take this equation because again I have v initial y, I've got acceleration, all that stuff. Now I'm looking for time. Vertical displacement is 0, set it equal to 0. I'm ready to solve for time. Take this term, subtract it from both sides. I've got negative signs on both sides. I also have at least one t term on both sides, so I'm canceling out a t term. So v initial y is 1/2 gt. Multiply both sides by 2. Divide both sides by g. I've got this expression for time. Okay, so a couple steps algebraically here. Subtracting this term from both sides, canceling out the negative signs, getting rid of this 1/2, multiplying both sides by 2, getting rid of g, dividing both sides by it, getting t by itself. Again, I'm using v initial in the y direction. Don't forget, 8.5 meters per second. Substitute 9.8 meters per second squared in for g, and I've got my total hang time. You could go back and use a kinematics equation, take this time, split it in half, right? Come over here, maybe plug it in here and find delta y. You should get the same thing, right? So split this in half, plug it back in here and solve for delta y again. You should get that max height. Again, everything in the y direction, right? Everything in the y direction. This is all independent of what's happening in the x direction. Part C is asking for the horizontal displacement of the object. So now I'm ready to talk about what's happening in the x direction. I'm going to use this. I need the total flight time, right? I need the total time the object is in the air because that's the total time it's moving in the x direction. So I've got this time, 1.73 seconds. The velocity is constant in the x direction. Again, I've got to go back up here. Talking about the x direction, I'm going to use this velocity vector. Not 20, I'm going to use 18.1 meters per second. Plug those values in, evaluate it, don't need any algebra, already solved for delta x, 31.3 meters. Again, this has nothing to do, the only thing that connects these two types of motion are the time. Right? The total time it's in free fall is equal to the total time it's displaced horizontally. Okay, so that's usually what connects these two equations, right, is the time. Okay, so the last part says find finding the magnitude and direction of the final velocity vector, right? So we were given this, and we have to find this. Now I see this diagram, right? I've got symmetry. I can do it the easy way. I can say v final is just negative this value, and then v final x is the same as v initial x. Okay, but again, this is just for symmetric problems. This is where the object lands vertically where it started. Okay, so I can make that conclusion in this, but I'm just going to go through it the hard way so we can use it for other types of problems. So I know, regardless of whether it's symmetric or not, the v final in the x direction is equal to v initial in the x direction, because I've got constant velocity. So I don't have to do anything with that. It's going to be 18.1 meters per second throughout the whole problem. Free fall in the y direction. Let's find v final y. Right? I want the magnitude of v final, so I want v final x, v final y. I already have v final x because it's the same as v initial. Let's use this kinematics equation to solve for v final y. I've got positive 8.5 meters per second in the y direction. Acceleration due to gravity. Total hang time is 1.73 seconds. You see this is negative, and this is actually twice the value of this. So if you just calculate this term, you should get 17, right? Something very close to 17. So what we end up with is 8.5 minus 17. Pretty sure it's 17. Double check that for me. But I'll get a negative velocity of 8.5 meters per second. So this kinematics equation just verifies to me that it's symmetric free fall, right? This time later, it's going to have a velocity same magnitude, different direction. I'm not asked to write it in component form, but again, it's still a good habit. V final is 18.1 meters per second in the x, negative 8.5 meters per second in the y. Throw it in your Pythagorean theorem, calculate the magnitude, we get the same magnitude. Okay, it's the same speed when it hits the ground as it was when it's launched. So take the inverse tangent of the y component over the x component. I'm going to get negative sign in there. I'm going to interpret it as below the negative x-axis because I've got a negative y component, positive x component. That makes sense with my model. I'm hitting the ground at an angle like this, right? I'm initially launched above the x-axis. I'm going to hit the ground at an angle below the negative x-axis, okay, or south of east. Right? I can call it south of east. All right, that's the same angle that it was launched with, right? Roughly, right? 25 degrees, right? As long as you ballparked it, right? We did some rounding stuff. I admit I'm kind of lazy with my, sig figs and stuff like that. Not a big deal. 25 degrees, and then about the same angle. All right. Alright, so my second projectile motion problem is I'm still launching a projectile, but I'm launching it off of a 100-meter cliff. Okay, so draw your picture, a cannon or something, shooting a cannonball off of a 100-meter cliff. Okay. Initial velocity, again, I'm given magnitude and direction, 30 meters per second, 50 degrees above the horizontal. So it's the same direction. Alright, different angle, same direction above the positive x-axis. We're looking for total hang time. How long is the projectile in the air? How far from the base of the cliff does the projectile land? Now we'll see that this is delta x. Okay, how far from the base of the cliff does the projectile land once I draw my picture? And then we need magnitude and direction of the velocity as it strikes the ground. We're going to describe the velocity vector the same way we always have, right? Is it below the negative x-axis, north of east, whatever. Alright, so we're going to give it some verbal description after we find theta. So I've got an initial velocity, 30 meters per second. That's the magnitude. I'm still going to have to split it up into its x and y components. Theta is 50 degrees above the positive x-axis, so my velocity components are both going to be positive. My displacement is negative 100 meters. Remember, I'm starting from an initial position of positive 100 meters. I like to say that the lowest point is y equals 0. That's going to come handy in like chapter 5 when we start talking about gravitational potential energy too. So this is the convention I like to stick with. Lowest point is y equals 0, y final minus y initial, so it's 0 minus 100. My displacement in the y direction is negative 100 meters. Split up your velocity vector, v cosine theta, you get v sub x. V sine theta, you get v sub y. Alright, so we've got our velocity components, right, in the x direction, y direction. Again, I've got, just like the previous problem, this is my setup. I've got constant velocity in the x, free fall in the y. This is how we set up any projectile. It's good to get in the habit, right? You'll have access to the kinematics equations like while you're taking the exam and stuff. Not a memorization type thing, but it's still kind of good practice to write it all out, you know, set your problem up, have these readily available. Okay, so this is what we're doing here. We get the same situation. All right, so it says find the total time in the air. This isn't a symmetric free fall problem, so I can't say delta y is 0. However, like I did with a previous free fall problem, I can use this equation. I know the vertical displacement, I know the initial velocity in the y direction. Again, this is v initial in the y. I know acceleration. I could solve this equation for time. It's a quadratic, it doesn't factor, I gotta use the quadratic formula. That's really annoying, but I'll do it anyway. Positive, negative, I'm gonna get rid of that negative one. Okay, so that's not a real solution. I'm gonna pick 7.4 seconds. If you're like me, this option 2 works especially well because we actually stumble upon some information that we need in the next part of the problem. So I'm avoiding the quadratic, and just like in that previous free fall problem where I gave you another option, I'm solving for v final in the y direction first. Okay, again, it's more work because I'm using 2 equations, but I'm avoiding the quadratic. And again, in this particular problem, it's especially useful because this v final y is necessary for the last part. So I use this equation because I've got the displacement, I got the initial velocity, I need the final velocity. So solve for v final, substitute everything. Remember, your displacement is negative, so this term's going to become positive. I've got v final of 48.9 meters per second. Our negative sign business, it's a v final in the negative y direction. Okay. So I wasn't asked for that, but again, in this problem, it's necessary for part 3. Now I can use this equation because I've got v final. I can use this to solve for time. Subtract the initial y from both sides. I've got a negative g still here. Divide both sides by negative g. Got a nice expression for total hang time. Substitute my values in. Don't forget v final is negative minus a positive v initial divided by a negative sign. I've got a positive scalar, 7.4 seconds. Same time I have over here. So option 2, I avoided the quadratic, and I'm just going to make a note of this because it's going to be necessary for the last part. What's the magnitude and direction of the velocity as it strikes the ground? So I need v final in the x and v final in the y. I've got v final in the x. Oh, sorry, I skipped this part. Okay, so we got to do part B first. It says how far from the base of the projectile, or from the base of the cliff, does a projectile land? Just like before, I've got constant velocity in the x. Now I know the total hang time, so I can just take the velocity in the x times the time, and I've got the horizontal displacement, 142.8 meters. So part C, I'm looking for the magnitude and direction, just like the previous problem. Velocity in the x direction is the same, 19.3 meters per second. V final is negative 49.8 meters per second. I got that from option 2. Now let's say you're fine with the quadratic, right? And you got this time. This is what you did to solve the quadratic, right? And then you get down here to part C, and they want magnitude and direction, and I got v final y. What am I going to do? I'm going to go back here to option 2. I have enough information here and here now because I've got the total hang time. I can use either one of these kinematics equations, this one right here or this one right here. I can use either one of those kinematics equations to solve for v final y. If you chose option 1 and used the quadratic formula to solve for hang time, that's what you would do. And find the final velocity, negative 49.8 meters per second. Now it's just converting a vector in component form, I've got the x and the y component, to magnitude and direction. Plug it in your Pythagorean theorem, get the magnitude. It's different than the initial launch speed because we've got acceleration in the y direction. It's not symmetric. Okay, it's actually moving faster in the negative y direction than it was launched in the positive y direction. So 53.4 meters per second. Find the angle. Negative y component, positive y component. Again, I'm in the 4th quadrant. So I'm hitting the ground in a direction that's being measured from below the positive x-axis, or south of east. So I get that angle, 68.9 degrees, below the x-axis, or south of east. Okay, so I'm going to upload this. This should be everything, right? This should be all the content for the first week. Exam 1 will be on Friday. I'll give you some details on how that's going to be administered, and it's going to be on all of the content from Chapter 2 and Chapter 3. Get this question a lot, and I don't directly address it in the syllabus. What's the best way to study for the test? Right? That's what you're thinking, assuming you've watched all of these long videos. Right? Now you're hearing me say that. What's the best way to study for the test? Do all the problems that you've seen. Do all the examples that I've shown you in the PowerPoint. Practice the WebAssign problems repeatedly. Practice the examples in the lecture repeatedly. Okay. Practice the examples in the text repeatedly. That's just the best way to do physics. Okay. Practice the problems. I don't discuss what's going to be on the test. Okay. I'll tell you the topics. It's going to be one-dimensional kinematics, vectors, and two-dimensional kinematics. Okay. So everything that you've seen up to this point, just expect to be prepared to have these types of problems on the exam. Okay? Alright, so I'll communicate extra information about the first exam on D2L. Alright, thanks.